As we look at 4.2, 4.2 deals with a subject called vector spaces. And when we looked at 4.1, we looked at a theorem 4.2, and it listed 10 different properties of vectors. And as we move on, it turns out that things other than vectors have these certain properties at times, and we'll look in the book. Here's a list of those properties, and we're going to expand it to something other than, could be other than just vectors. Could be a matrix, could be a polynomial, but if it has the same properties as vectors do, then we'll consider it a vector space. So remember, for example, if we took two vectors and added them together, we got a vector. If we took two vectors, we could add them together in either order. The associative property was accurate under vector operations. We had something called a zero vector, where if we added that to a vector, we got our original vector. We had the opposite of any vector. For example, if we have vector 2, -4, -2, +4 is also a vector, and if we were to add those together, we get 0, 0, which is the zero vector. If we multiply a vector by scalar, we still get a vector. We could use the distributive property for vectors. If we have two different, this is just another form of the distributive property. 7 is distributing a scalar. 8 is distributing two scalars, or basically a vector times two different scalars. 9 is associative property. If you have a scalar times another vector, it doesn't matter which order. And then you have basically an identity vector. So if we look at a vector of any size, all vectors are going to have those properties. If we look at a vector that is in R3, meaning that it has 3 dimensions or 3 components, all of these properties are going to hold for vectors with those descriptions. If I take one vector x, y, z, I can add another vector u, v, w, and if we add their corresponding components together, we still get a vector that's 3-dimensional. Now, if we added those together and somehow got a vector that was 2-dimensional, then it would fail to meet these characteristics, so that would break the characteristics of a vector space. And we'll look at some examples later of some things that fail to meet these characteristics of a vector space. But no, all of these are just going to be numbers, so we can add any real numbers together and get another real number, another real number, and another real number. So that'll give us something that's in 3 dimensions. Even something that's in 1 dimension, that's just basically the set of real numbers. If I take some real number and add another real number, then I get a real number. I'm going to get something that's still in that set of real numbers. I'm not going to get something that's out of that set, something that has completely different characteristics. The commutative property holds if we add 3 different real numbers, it doesn't matter the order we add them. If we add 0 to it, we get that number. We have an opposite, and then all of these of multiplication hold true. So basic things, 1-dimensional vectors, 2-dimensional vectors, 3-dimensional vectors, all of these things are vector spaces. things that may not be vector spaces that are vectors are things that are given more precise definitions. For example, if we say let V be a set of vectors such that they have this characteristic to it, it turns out this is not a vector space. Now let's see why the set of vectors with this characteristic where x is any real number, why that's not a vector space. So an example, let's suppose we have the vector 2, 1 and the vector 3, 1. So our first component is any number, the second component is a 1. Notice if we add these two together, we add the first components 2 plus 3, the last components 1 plus 1, and notice our answer is not in our vector space. It is not in what we defined as our space. So hence, this is not actually a vector space. We added two things that were in this set, and we got something that was not in the set V. So as long as all the things that we're adding together give us something of the same nature, then it's a vector space. But if we have some things that once we combine them can possibly give us something that is not like the rest, then that's not a vector space. Let's look at an example. Let's say we have 2 by 2 matrices of this form. And we say that our space is all of the 2 by 2 matrices of this form. And let's see if that would indeed be a vector space. Well, if we took random matrices that met that description, the only thing that we're restricted by is that the second row, second column entity has to be 0. A, B, C can be an element of the real numbers. It can be any number imaginable. So if we add those together, 1 plus 2, 2 plus 1, 3 plus negative 2, 0 plus 0. So we get real numbers for these components. We get a 0 for the second row, second column component. And notice that'll always happen, no matter, as long as we take two matrices that have a 0 in the 2, 2 location and add them together, we'll always get a 0 in that position. It doesn't matter what the other ones are. If we were to take this, multiply by a scalar, we get 2, 4, 6, 0. Notice we still have real numbers here. That is 0, which is what is required. So it meets our requirements. And if we go down through each of these, we can change the order and we'll still get 0 in that 2, 2 location. If we add 3 vectors, it doesn't matter, or I say 3 2 by 2 matrices, doesn't matter the order. The 0 vector, which in our case would be the 0 matrix, notice that is in this space, in this set, because it doesn't matter what A, B, and C are as long as the 2 by 2 is a 0. So all of those are good so far. We have an opposite. If we take that, okay, -1, -2, -3, 0. That's in the set. Sorry, I circled the wrong thing. Notice if we have A, B, C, 0, and we add the opposite of any real number is still a real number. So all of those are okay. When we add those together, we get 0, 0, 0, 0. So basically there is an opposite of each of these. We already looked at scalar multiplication. All of those will hold true. So this one is fine. This is a vector space. While this doesn't look like a vector, it has all of the 10 characteristics that work for vectors. Hence, thus, it's a vector space. Now let's look at an example of a polynomial. We have a polynomial in the form ax plus b, where a and b are any real numbers. So basically the set of linear polynomials, these, let's see if this makes up a vector space. So I'm going to pick another one. And let's think about, well, if we add these two together, will they always be a linear polynomial? So if we were to add these two together, so if we added these two together, we would have a plus c times x, and this doesn't need to be the same letter. So what would make this not a linear polynomial? So this is what we defined our space to be, the set of all linear polynomials. And in order for it to be a vector space, if we add any linear polynomial together, we must be able to get another linear polynomial. Now, notice if a plus c equals 0, then we have 0x plus b plus d, which is b plus d. That's not a first degree linear polynomial. So if we, I guess maybe we should be more specific when we say linear. Maybe we should say a first degree polynomial. Notice that would not be a first degree polynomial. And there's nothing in our definition that says that we can't have two numbers that add together to be 0. So, in other words, this is not a vector space, because it is possible to add two things together in this set and get something that's not in that set. So this first section is just kind of an introduction of what vector spaces are, and basically you're going to be given a set and asked, is it a vector space or not? And in general, you're going to be looking and trying to think up examples of what would make it or make something out of the set. Now, just because you can't think of a counterexample doesn't mean that there isn't one, but for most of these, hopefully it'll be fairly obvious of something. If it's not a vector space, hopefully you'll be able to quickly come up with an example of something that um, when you add them or multiply, you'll get something that's out of the set. So that's all you have to do to demonstrate, hey, this is not a vector space. List a counterexample. Now, since this is a 200 level course, I'm not going to make you do a full proof. If we determine that something is a vector space, I might just get you to on the test make a brief description of why it is a vector space or why there are no counterexamples. But in general, I would just want you to be able to recognize, is a particular set a vector space or is it not? And it'll always go back to, for that particular set, do these 10 axioms or do these 10 definitions hold? Sometimes if we restrict sets too much, it takes away their ability to be vector spaces. Sometimes if we don't restrict things enough, it keeps them from being vector spaces. We look back at this one, by restricting this row 2 column 2 component to be zeros, and by letting all the other components be any real number, that allowed this to be a vector space. Here we didn't make any limitations on our coefficient of x, our coefficient of b, and that ended up making something that was not a vector space. So let's look at another example real quickly before we wrap it up of something that's essentially over-restricted. Let's suppose we have the set of ordered pairs x, y, such that x is greater than 0 or equal to 0 and y is greater than or equal to 0. Let's see if this is a vector space. Now, if we just think about adding 2 together, if we add 2 positive numbers together, we're going to get a positive number. If I add 2 more positives together, we should get a positive number. So we're okay with the first criteria. If we change the order, we're okay with that one. These two things mean the same. In the real numbers, x plus a plus x, those are equivalent. Y plus b, b plus y, those are the same. So if this is not a vector space, we need to think which one of these is going to give us a problem. And often, if we restrict things to be only positive numbers, one of these that's going to give us trouble is this one, because we have to have an opposite of all elements in our space, such that when we add that the element and its opposite, we get 0. Well, if we just make up an example, if we have 2, 3, which notice the x and the y are both 0, then to be able to add something to that and get the 0 vector, we would have to have a -2 here, a -3 there. But notice this is not in that set, because the x is not positive, the y is not positive. Thus, this is not a vector space. So you might have noticed this is called closure under addition, basically saying that we have a closed set. If we add anything together, then we're not going to get something that's outside the set. If we subtract, we're not going to get something that's outside the set. It's closed. It has boundaries. We don't get outside those boundaries. So that's what a vector space is.